All right, so as I mentioned, this is week 8 of 8 of our level 2 CAD class. So finally here, we made it. And what we'll do today, like I mentioned before, we're going to wrap up our keychain kind of free creative design project. I'll start off just by talking a little bit more about some selected topics related to 3D printing. I'll take a brief moment. I'll give you some time to work on your projects and ask any questions if you have them. I'll try to fit in a little demo related to Fusion, which is something that I'll show you. And at the end, maybe at the beginning actually, if you have any, I asked you last week to come with any questions about things you wanted to see in CAD, in Onshape, or in general. So I'll make some time for those questions if you have any prepared as well. All right. So I guess before I get started with 3D printing stuff, I guess there's two of you here. Did either of you have any questions or prepare any questions of things you want to see in CAD? So it can be like how to use any of these functions, how to make a specific object or type of object, how to do something, anything like that. And if you don't have any right now, you will have another chance later. I expect like there will be a bit of time where you'll just be working on the project. So during that time, if you come up with anything you want me to show you, feel free to ask. So yeah, just keep that in the back of your head. And all right, so last week we talked a bit, just starting to introduce the idea of using CAD and how to, things to think about when you're designing a part for CAD, for printing. I guess so then we talked more about how you should consider using the 3D printer. We're going to kind of focus today more on things specifically that you need to do in your CAD that will make it better suited for actually building it with a 3D printer. So the main one there is kind of related to something that I mentioned before, which is your minimum wall thickness. I'll explain a little bit more about some things related to 3D printing, but it'll be a pretty light day. So we'll start off, if you're not familiar with how like a typical 3D printer works, if you're getting something just like off the shelf, household, desktop, hobby printer, it probably works by a mechanism like this, known as like fused deposition modeling, or FDM. And the way this works is, let's see, the material that you're actually building the part with will come from a big spool of like the base material, whatever plastic, PLA or ABS that you're using, and it gets fed into this nozzle here. So the material, the stock for it, the source is that spool of filament, but when it actually comes out, the size of the deposited material, that's going to be determined by the geometry of your nozzle. So you can imagine the size of the nozzle kind of has an impact on the quality and feature characteristics of the part that you're going to get out of it. So mainly what we're concerned about is like this diameter here, kind of the hole that the extruded material is going to come out of. And this will kind of impact your layer thickness and the minimum part thickness. So you need to make sure that you know what this is and to design your part accordingly, because if you design something that's too small or things that have features that will be too small, it probably won't come out very well when you try to print it, and it can even cause the print to fail depending on what you're doing. So yeah, if you remember a couple classes ago, I showed you the measure tool, which is down here in Onshape. And so what you're probably going to try to do, you just want to make sure that the thinnest features that are on your part have a minimum distance, a minimum thickness that is greater than, maybe a couple multiples of whatever your nozzle width is. And that way, when you actually print the material, you'll make sure that you have enough resolution with those lines to actually produce like a faithful representation of the model, and also factors like having enough strength and things like that. Let's see. So I don't believe Onshape has like a simple point-to-point measurement, but if you ever need to know like the distance between two arbitrary points, something you can do, just create a sketch. You can plot your points on the part that you want to know, like distance between, for example, and then like if you're actually doing this, you'd like make sure to constrain this to be on the part edges and so on. And then you can just go back and measure, for example, the distance between these 2 points. There may be a better way to do it. There might be some kind of built-in point-to-point measure type of thing, but if in the worst case, you can always do something like that to determine where your thinnest features are. Other things to watch out for are like these narrow cusps. These might come out okay, but there's a chance like around here, the material might like blend together. Likewise here, I mentioned before, the ears might be a bit of a problem area. And if you're doing things like text, if the text is too small, if, for example, you have some letters and like the holes in the letters or like the actual width of the letters is too small, then based on the resolution of your printer, it might just come out as a bunch of garbage. It'll just like, it either won't come out at all or it won't look the way that it looked in your model. All right. Here's something that I mentioned before. When you print something, most of the time, you're not actually going to print things like completely filled, because that would use a lot more material than is usually necessary for most things. And it would be a lot heavier, right? So there are some cases when you do like completely fill in your part. For example, if you're going to be like post machining or like modifying your part after you print it. If, for example, you want to tap threads, which we talked about using like a tap, then you would want to have like a completely filled section so that there's enough material there to actually create those features. But otherwise, you'll just have some different patterns inside, which is controlled by that program that I mentioned, the slicer, which is what prepares your 3D model for the 3D printer. It kind of creates a program that the computer follows to lay out all of those layers. Here's some other things that I think are interesting, some things that are good to know about and that you might do if you ever have to operate or manage a 3D printer. One of these things is benchmarking. So there's these things called standard, maybe not standard, but there are these artifacts that you can find models for. I think on Thingiverse, there's a lot of these like print test artifacts that you can find if you search for things like that. But the idea is it's a part that has a lot of interesting features that will reveal to you how capable your 3D printer is. So here in the far back corner, you can see there's a number of like small pillars and some thin walls like next to each other. So it'll show you like how well is my printer able to create these like small patches, these small area layers and stack them on top of each other. Like how straight will these pillars turn out? You can see there's a lot of text here. So like you can see how good is the resolution on small text, like how small can I write letters? Same here with cylinders, different grooves. This is like an overhanging section. So it'll show you, there's an overhang test that lets you see if your printer is able to do these overhangs without like the support printed under it. So like what's the most dramatic distance or angle that you can have overhanging and still get a good quality. You can also see like your print faces at different angles. So here you can see this artifact has markings at 10-degree angle increments. So every 10 degrees, you can see how does the quality of my surface finish change as I, print at a different angle. And you can imagine like it's probably pretty good at 10 degrees and kind of gets pretty bad at 80 degrees when it's done without support like this. Yeah. And it's interesting, you can actually find like real like official standardized versions of these that are used in like research papers when they're experimenting on like new methods of 3D printing. There are like standard artifacts. So that's pretty cool. Other things, I mentioned this last week, there's a lot of ways where your prints can fail, and when it does fail, you might get something pretty catastrophic, pretty interesting looking though. So there's a lot of reasons why that can happen. Things to look for, it might be like you want to identify where the problem occurred. What did you do wrong, and like where did you do it wrong? So it could have been during the design phase when you're still in Onshape or whatever CAD program and creating your design. So you want to see like, did I design aren't very good for 3D printing? Like no matter how I orient it, there's going to be these really severe overhangs. Or is it a feature that's way too small on some part of my geometry? Things like that. And you can consider modifying your design itself in CAD to improve how well and how quickly it can be printed. Another thing that could have happened is that the error happened, I guess, under the umbrella of printing error. When you're still in the slicer program, so you've already gotten your model file, you already have your 3D design, but you're preparing it, you're telling the printer how to print this thing. During that stage, it's possible to make some poor decisions or make some mistakes. For example, things like print orientation. We talked about last week how you want to consider things like which way the layers will be and how that affects your material strength, or like how quickly it'll print, depending on if you have a really tall part standing upright or laying flat on the table. So you can have some printing related errors at that stage. You can also have printing related errors due to actual mechanical issues with the 3D printer itself. So 3D printers, especially the cheaper and on the hobby level, are pretty notorious for having issues. So Could be something with the software, could be something, if you don't have the settings correct, if there is something wrong with the environmental conditions, your parts are getting old, you might run into some issues, like the nozzle is not getting hot enough. You might get issues that lead to things like what you see on the right, where the extruded material isn't sticking that well to itself, or when you're rapidly traveling between different features that shouldn't be connected, there's still some melted strings of material that kind of follow the printer head around, which causes kind of like excess stringing all over your part workspace. Your nozzle can jam, which is pretty bad. But as with anything, the goal is to learn from your mistakes. There's nothing too catastrophic that you can do compared to, say, machining, where you're spinning these metal cutting bits at thousands of RPM. Thankfully, it's a bit safer. I guess on that note, you need to kind of be careful with certain plastics. They can release gases and things that you might not want to breathe in. But for the most part, it's like physically safer than some other forms of manufacturing. So learning from your mistakes, that's what you want to do. All right. If you're interested academically in the idea of 3D printing and things related to 3D printing, there's a lot of controversy, which you may or may not know about, related to 3D printing. It's not everyone loves everything about 3D printing. And so if you're interested in reading about these kinds of things, you can find a lot of literature and I'm sure media about 3D printing of weapons. So, when you can't really control what people make with their 3D printers, of course, there can be some bad actors who try to make weapons with 3D printers. Other thing is intellectual property rights. So you might be familiar with things like copyright law, with patents. So, for example, the reason you can't find every book ever written online is because of intellectual property laws. And in a similar way that like books and people's writings are protected, so also are people's designs. So there's a lot of talk about how or what we can do about people who try to 3D print things that aren't their intellectual property. And so they technically are not supposed to print, but they're able to print it nonetheless. As you can see, there's a lot of ethical implications related to 3D printing. Other things, if you're more interested in like the scientific side, which I know I am, there's a lot of new 3D printing techniques that are being developed that help to improve the feasibility of using 3D printers in more industrial applications. So you'll notice like a lot of 3D printing is relegated kind of to the hobby side. It's more for fun or for doing smaller scale projects. You'll notice that like in your car, for example, you won't really find 3D printed parts in your car just because it's difficult to manufacture parts with the tolerancing and strength that you would need in an application like that. At the end of the day, methods like casting and machining just do better in precision and strength, but that might not always be the case. We're getting a lot of new, they're not all technically 3D printing, but they're all methods of additive manufacturing that are starting to gain some traction. A lot of research is being done in characterizing and inspecting these additively manufactured parts so that they can one day be used in these like more, I'll say, industrial applications. So I forget if I showed you this, but there's like laser related techniques that can help you, allow you to actually print things out of metal. Yeah. So it's actually, we have this technology now to essentially additively manufacture any geometry we want in metal, which kind of has a huge potential because traditional metal manufacturing techniques are kind of limited in that you can't do a lot of these complex internal features if it's not possible to make it with a mold, or if it can't be reached by a machine, a CNC machine. But with these new techniques, we're going to be able to design hopefully lighter parts, ultimately parts just as strong as those made with conventional techniques, but hopefully done at a smaller time and cheaper scale. Although that's probably a long way off just because of the advantages conventional manufacturing has in that respect. Anyway, so yeah, metal 3D printing, that's a thing. It exists and you should know. There's also composites 3D printing. So if you're familiar with things like carbon fiber, if you're a fan of Formula One, like racing, you'll know that a lot of composites are used to make the chassis or monocoques of these vehicles, just because they're really strong but still really light. So it's actually starting to be possible to just print composites, which is pretty crazy because that could potentially save a lot of time involved in doing layups and like creating the molds and such for these composites structures. There's some fun things you can do. There's like food 3D printers. I think chocolate 3D printers are a thing. So yeah, it's always entertaining. And there's also starting to be some medical uses of technology that is similar to 3D printing, right? So it's very exciting. A lot you can expect from the future, and it's always good to keep an eye out on current trends and what new research is being done in these various fields. All right, so do you have any questions about things related to 3D printing? If not, I'll give you some time just to work on your own on your keychain project. And like you don't really have to think of it as a keychain per se. Like it's just more of a free design project for something that you could potentially 3D print. So I do want you to think about things like your minimum wall thickness and like total size. But beyond that, just try to do something interesting. Try to challenge yourself. If you have something, if you're already finished your keychain or you're happy with what you have, just try to make something, right? Like personally, when I first was starting to learn CAD, what I would do is just look at random objects that were around me on my desk, things like my computer mouse or my phone, and just try to model those, try to recreate those as closely as I could in the CAD program. So at the end of the class, since this is our last class, I will spend a few minutes talking about things you can do, where to go from here, or like how you can keep learning. But yeah, for now, just like try to model something interesting. So I'll give you some time to do that. And while you're doing that, I'll prepare a quick little demo in Fusion, which hopefully works. And I'll also try to upload these slides, which I was having some trouble doing earlier. So yeah, work on that for now. Let me know if you have any questions about anything, and I'll be back with you in a few minutes. Also, if you want to share what you've made, you're also free to do that. Just doesn't have to be now, just whenever, if ever you want. It's fine if you don't. All right. So does anyone have any questions or like anything about CAD in general, about Onshape? Do you want to share anything that you've made? And it's all right if you don't. All right, so hopefully you're more or less wrapped up with the project. I don't know if like the AOE Center has some plans. I guess if you can go there physically, you can like ask about possibly printing your part, and whoever's running the printer there can help you with that. I'm gonna take a moment to do a quick demo, and I'll show you an example of how like a slicer program might work for 3D printing, and I'll show you like a few options that you might have for how you can do CAD that's not Onshape. So I guess one option, which like I'd say is pretty good and should be free to you, is made by a company called Autodesk. So you can just like look for Autodesk. They're pretty famous. They have some like pretty well-known products like AutoCAD and Inventor, which you may have heard of. But if you are a student and looking at their website, it seems like if you're a middle school or a high school student, you should qualify to be able to create an educational account, which will give you access to a lot of these software for free, which is really great because they're like pretty like they're quite solid. They're very widely used programs. And so in particular, I use a bit of Fusion 360. Tinkercad is probably also a good like entry level 3D design and 3D printing type of application, but I happen to have Fusion installed right now on this computer. So yeah, like you can also like create an account and install the program if you so choose. And I would say it's a good idea early on to try out a lot of different CAD programs. Onshape is like very unique in that it's all built into the browser. I think it's the only one that has something like that. Kind of think of it like the Google Docs of CAD program. But in almost all cases, these CAD programs that you'll work in will have their own application, right? They won't be in a browser like this. So if you're interested, like one thing you can start out with that's free is Fusion. So hopefully you can see this on my screen. This is kind of what it looks like in here. I have something up for something else, but Fusion, kind of similar to Onshape, has like a integration with the cloud. So your files are kind of stored on their servers. You kind of have access to all your files wherever, like whatever device you're using it on, which is different from, again, like a lot of other CAD programs, which kind of rely on actual files on your computer or on your own like computer or network. But Fusion like is kind of on the cloud. So you can see this is kind of the design space. This is like my document or my part studio, if you were to compare it to Onshape. So you can see like it looks really different from Onshape, but the idea is that the things that you can do here, the way that you create parts is pretty much the same. And hopefully this shows you that with the skills you've learned so far, after you learn the basic like movement controls and commands and things like that, you have all the knowledge you need to be able to continue modeling things at the level that you're able to in Onshape or any other program. So here you can see like there's my navigation cube. It looks a little bit different, but I can move things around. I can pan. I can select things, zoom in and out. And so, hopefully this is very familiar. The first thing I can do is create a sketch, same as Onshape. I pick a plane to put the sketch on, and then I have my tools. These should be pretty familiar to you. This is my line tool, it makes lines. I have my 2-point rectangle tool. It works exactly the same as the Onshape one. I have a circle tool. And as you keep looking through this, there's a whole bunch of tools that are, as a sum, kind of achieving the same thing that you're able to achieve in Onshape, right? So I can say like finish my sketch. Then I go back to my 3D workspace. I have my tools here. Extrude, revolve, they work exactly the same as they do in Onshape. It's just the interface is a bit different. So I select my region or sketch profile, and then I can extrude it to some depth that I want. And that's how I create my 3D bodies. So nothing I did there should have been that like revolutionary to you. Like everything looks different, but the things that you're doing is the same. So once you start using CAD for school or your other competitions and you're not using Onshape, whether that's like SolidWorks or NX or Rhino, Creo, CATIA, there's all different kinds of programs, but more or less they work in a similar way. You can see I have my fillet tool. It does the same thing, creates fillets. I can do assemblies. The fusion assemblies, in my opinion, is a bit weird, but it's the same idea where you have, they call it joints, but you're just creating rules. You're creating restrictions on how your components are allowed to move with respect to each other. Like there's measure tool, just like the Onshape one, tells you things like distances. So that's that. This is something that you are able to do. Like you don't have to, as long as you're a qualified student, which I expect you are, you can use this. One other thing I wanted to show you is how a slicer program works. So one of the cool things about Fusion is that it has built in a pretty solid CAM and like a CAM package, computer-aided manufacturing. So we talked about 2 weeks ago, like for manufacturing, if you're trying to program a CNC machine to do your thing, make your part, you need to create a program to tell the computer what to do. And so I personally did use a bit of Fusion to control CNC machines while I was at school. It turns out Fusion also has like a 3D printing slicer of sorts. So this probably won't be your slicer of choice. There's probably a lot of other slicer programs that might be preferred by whoever owns your 3D printer that you'll be using, but just to show you like what it does, just to show you the ideas. I can select, oh boy, I can select like the 3D printer that I have. I don't actually have these 3D printers. They're just some default options that show up, but you can either find or create like the specs related to the specific 3D printer that you have. And once you do that, whoops, let me do that one more time. I can select it for 3D printer. The operations I'm doing is an additive manufacturing. I hit OK, so that creates my kind of work setup. And then what I need to do is kind of arrange my part where I want it to be printed on my build plate. So I can kind of move it around. If I'm doing multiple parts, maybe I kind of want it to be off in a corner. I might want to rotate it. For example, if I think for whatever reason, I think mechanical strength is more important in, the, I guess, y direction, this coordinate plane. If I'm trying to resist blows in the y direction, or the x direction rather, I might want to print it something like this. But as you might realize, the fact that all these holes and things are here means that the best way to orient this thing is probably lying down on its back like this, because that just means that every cross section is going to be the same geometry, right? So you can move around your part, you can orient it how you want. Then you want to make sure that the part is touching your platform, which for me it is already. You can control things related to your printer. So let's see. Hopefully you can see the dialog box that pops up. You can specify basically a bunch of things that tell the slicer program about your 3D printer, right? Like your 3D printer is going to have all these different properties, and the slicer will make various decisions for you when it's creating a program based on what it knows about your printer. Infill is something we talked about. So you can say like, oh, what kind of pattern should what kind of pattern do I want the program to use in the filling shape. So I can specify like how densely filled the part should be, like the raster angles, things like that. Here, things like supports, rafts, additional things that aren't built into the like basic geometry, but still might be necessary for the print itself. I can place supports if I have overhangs. I can do things like that. And then you just tell it to create a program. And what this slicer program is going to do is it's going to generate this code that your 3D printer is then able to accept and execute to print this part. What's neat is that Fusion also gives you like a, whoops. Fusion lets you simulate things, which is really handy, both for the machining thing, and it's pretty cool to look at for the 3D printing thing. So you can see layer by layer how the 3D printer is going to build up this part. And if you've never seen a 3D printer working before, hopefully it gives you a good illustration. Basically, it's just showing like layer by layer. It doesn't show the 3D printing head or anything. It just shows you how the printer deposits material. So this is going like way, way faster than it would in real time. You can see like every time more material is being added, it's kind of being highlighted. You can see it's just tracing out these shapes. It's filling in the inside with the honeycomb pattern, which I told it to. It's just going up in Z one layer at a time. I'm just continuing to work on this part. And during this whole process, I can like look inside, kind of see what's happening. And if there's any issues, if something's happening that I didn't expect or don't want, then I can go back and fix my settings in this part, or go back to my design and change my 3D model itself. You can see now it's filling in the top. You can see how it kind of like crisscrosses those layers. But yeah, that's just an example. Most slicer programs, just like CAD programs, are going to look different. They're going to ask you for different things, behave differently, but at the end of the day, it's doing the same thing. All right. So that brings us to the end of our 8-week session on CAD and a little bit on 3D printing. Hopefully throughout these 8 weeks, you've learned, if you weren't familiar with Onshape, you learned how to use Onshape. And even if you were familiar with Onshape, hopefully you've built upon and expanded your fundamentals, your basics for how to go from creating like a 2D sketch to making a 3D object, combining 3D objects into an assembly, how to properly constrain things. One of the big things that we hopefully practiced in this session, like in this class, as opposed to CAD 1, for example, is learning how to look at a drawing and how to recreate like the dimensions and things from the drawing. That was one of the goals. And in the last couple of weeks, hopefully you've learned how to design a part that's suitable and could be 3D printed. In terms of where you can go from here, there are a couple more CAD classes that I may teach in this program, so you can keep an eye out for those. In the event that I don't end up teaching those, like I said before, the way that I learned how to use CAD was just looking around me, thinking of interesting objects that I can try to challenge myself with. Like they can be like normal household objects. Maybe you're interested in like making models or things like that. You can try making that kind of thing for yourself. This is something that I found really interesting when I first was learning. SolidWorks is another CAD program, very well known, but they have a yearly event called SolidWorks World, but at that event, they have an event called Model Mania. And basically they just release these challenging drawings and people compete to see who can create these drawings and like a modified version of them the fastest. And so there's this like page here that just collects all of these drawings. So you can see like if you want more practice reading these drawings, it's a pretty great way. These are all like pretty challenging, but they're all doable, right? Like I expect that given the tools that you've learned up to this point, you may need a few more tools. You may need to mess around with learning how to use planes and things like that. But there's plenty of information out there, like video guides, books. And so really like there is so many resources available online these days that if you're really interested in learning how to use CAD programs, there's really no limit to what you can do. So hopefully I can give you kind of a, like I've given you a bit of a starting point, like you know how to use Onshape now, you know where to go from here. You can try exploring different things like Fusion or other Autodesk products that you can get for free as a student. Try to look out into your school, see if they offer anything. But yeah, really just the best way to improve at modeling things, doing CAD, is to practice a lot. And that's all I can really say at the end of the day. Just model a lot of things and you'll get better at modeling things. It's as simple as that. As you try to model more complex things, there will be more and more things that you don't know how to do. And whenever there's something you don't know how to do, you can figure it out from some resource or another, and it'll just keep building on. So yeah, hopefully you had fun, hopefully you learned something. That's all I have for you guys for this session. So have a great summer break, guys, and maybe I'll see you again in the future. Let me know if you have any final questions. Otherwise, you're free to go.
Thank you. Bye.
Yep.
Thank you.